Hi, my name is Rob Boyko Mineral Exploration, and this is an introduction to the fine art of fire. I always pick topics from the questions that people ask me when I'm working out in the field or at times in my backyard. This series of presentations will be broken down into several smaller presentations to make it more understandable for the average placer or hard rock miner. I know that these presentations are a bit boring in terms of presentation, but I hope that you will get some insight into the subject matter and try the art on your own. I do recommend, however, that if you do try practicing this art, that you will do it outdoors or within a shop that has good ventilation. This is for the reasons of your own personal health and safety considerations. This art has been practiced since the time of the pharaohs and possibly even before them. A fellow by the name of Agricola was the first person to publish papers explaining the methodologies of this fine art. This art is still practiced today, and its methodology has not changed much throughout the millennia. This fine art is referred to today as fire assay. It is a classical technique used for the separation, pre-concentration, and refining of precious and noble metals. It is not confined to the precious and noble metals, but is mainly used for them. It is also used for analytical analysis of purity and load concentrations. It has many uses, but for the small placer or hard rock miner, it is a very useful tool for the collection and refinement of the gold and platinum group metals. When working with your concentrates and higher grade materials, this is a classical technology that is most appropriate for the collection and refinement of these metals. Let's take a step back for a moment and talk quickly about precious and noble, referring to the ores that you, as miners, are more interested in. These are the platinum group metals: platinum, palladium, osmium, iridium, rhodium, and ruthenium. Gold is a noble metal, as it is reluctant to combine with non-metals chemically, and it has a reluctance to tarnish. Silver, along with gold, including the platinum group metals, are all precious and rare. These precious metals and noble metals are said to be abundant in the Earth's crust, but they are rare. These metals are spaced unevenly throughout the ore's matrix. They are not evenly distributed, usually found in quartz veins, pyrites, and other lode bodies. Some are malleable, meaning that they are very soft and can be easily shaped or even pounded into fine sheets. And some are even ductile, meaning they can be easily pulled apart, forming long string material without breaking. Gold is one such metal. The question, though, is, are they free milling, or are they refractory? You are familiar with free milling gold. This is gold particles such as nuggets, flakes, pickers, all of which can be easily separated from the garbage material either by sluicing or crushing and so on. Refractory gold is not free milling. The gold particles are actually trapped in the rock's matrix. Ores such as sylvanite will have this characteristic. Because fire assay is a total collection process, both refractory ores can be broken down, allowing for the liberation of that trapped gold and other precious metals along with it. It is also used for refinement of your gold and silver. The statement that the finer the gold particle, the purer it is actually a true statement. For fire assay, 80 mesh or finer is ideal. Larger sample sizes make for better analysis when wanting to get an idea of how much gold you are losing during your panning process, or how much there is in metal within your hard rock specimens. Fire assay will give you an idea of whether your tailings are worth selling to processing plants or not. More on this subject on a later presentation within this series. I would like to briefly discuss something that you are probably familiar with, and that is gold. The word itself means yellow. It came from a Sanskrit word which means shining. In Latin, the word aurum means glowing dawn, and in the periodic table, the symbol for gold is Au. Gold has a specific gravity of 19.3 and melts at 1064 degrees centigrade. As mentioned earlier, it's malleable as well as very ductile and is considered one of the most densest of the precious and noble metals. It is also easily fusible with other metals and is inert towards most of the natural occurring substances. Crystals themselves are face-centered cubic lattice in structure. As mentioned, it is widely distributed throughout the Earth's crust and our global waters, but it is already mentioned as being scarce. The average crystal abundance is only about 0.004 grams per ton. In other terms, around 4 parts per billion. You are probably more familiar with gold as being nuggets, flakes, scales, crystals, and flour. However, in most cases, it is found as a natural occurring alloy, such as electrum, which is a type of silver ore. It also forms in solid solutions with copper, nickel, and the PGM groups of metals. There will be a few metals that gold will actually fuse with in nature. Small amounts of gold will actually substitute for other metals in a few minerals. Aristobite, calverite, and sylvanite are the most important ores. There are a couple more as well which are but lesser and important, such as petsite and agate. As placer, hard rock miners, and prospectors, some of you are new to the industry, in some cases as a hobby. Gold, as most of you know, can be found in those sulfide ores as well. Ores such as sulfides that contain native gold and quartz. However, it will show up in ores like sphalerite, which is a zinc sulfide, chalcopyrite, which is a copper iron sulfate, cinnabar, which is your mercury sulfides, pyrite, which is your iron sulfide. You got relgar, which is arsenosulfide. That means it contains arsenic. And you have elistite, just to name a few, which is actually thallium sulfate. And there are others. In regards to the concentrations, gold has actually been found in pyrite to be several hundred parts per million, actually. However, in arsenopyrite, it can actually be well over 10,000 parts per million. Gold can also be found in oxide ores such as limonite, calcite, clay minerals, and other iron oxides. Even though gold is commonly associated with the sulfide minerals such as copper, iron, silver, arsenic, and so on, I have to point out that gold is occluded in the rock. That is, it is free milling, which means that it will not or does not enter the crystal lattice as a molecule. But there are exceptions, such as the telluride ores and the argentiferous gold sulfide ores. Gold itself will not chemically combined, but it will alloy with naturally, that is, with other metals during its formation. And it will contain impurities of varying amounts such as arsenic, antimony, mercury, silver, sulfide, the PGM group minerals, and more. Regarding gold ore types, you might find an abundance of quartz and chalcedony, which are ubiquitous and ultimately associated with gold-bearing ores. The choice of processing, which is used to pre-concentrate or collect your final products, is all up to you. It's yours, all based on the ore type as well as your acquired knowledge. I have to point out that fire assay for analytics and refining is the usual tool of choice. To the mineral assayer or laboratory technician, fire assaying is a quantitative chemical analysis of the noble and precious metals with some variations in analyzing other metals. These would be in ores, concentrations, and other mining-related materials such as tailings and wastes. To the average small placer or hard rock miner, or even the prospector included, it can be said that fire assaying is a collecting and refining process for the collection and refinement of the noble and precious metals. Gold and silver and the platinum group metals, such as platinum and palladium, are all valuable as commodities. It is therefore a good tool to use to determine if the concentrates or ore bodies and lodes are worth the effort. Because these commodities have high intrinsic values, it's worth sending your samples to the laboratory for an accurate and precise analysis. However, it is expensive, and it may be worthwhile to do a preliminary assay to determine if the cost is warranted. This you can do yourself. In the laboratory, the technician may use solutions chemistry, which involves dissolving your specimen into a solution and then precipitating each metal of interest or simply run them through some type of analytical instrument. However, in fire assay, we use dry reagents to react with the sample by forming a solution of molten material. These reagents are referred to as fluxing material or simply fluxes. There are 3 stages to this method, which is also used to refine the collected metals of interest, which is more suited for a small miner's requirements of collection and refinement of the minute gold and silver particles, as well as the separation of the platinum group metals. There are 3 stages, better known as processes, which are used to complete the collection, refinement, and subsequent analysis. In order, the first is fusion, then cupellation, which may include inquartation, and then followed by parting. The fusion process is simply performed by taking anywhere from 10 to 50 grams of material, which is pulverized or screened to -80 mesh. This could be your concentrates or your sample. This is then mixed with the right amount of flux material to create what is known as the charge. This charge is placed into a suitably sized crucible and then melting that material in a fusion or muffle furnace at a temperature of about 1050 degrees centigrade for about 40 minutes until it's completely molten. This melt is then poured into cone molds for cooling, which forms a solid mass consisting of gangue material and a lead button, which contains the gold and the silver and any present platinum group metals. The lead button can then be easily removed from the slag for further processing. Although this process is simple in concept, the procedure is a little more complex and will be discussed in a future presentation. The cupellation process is stated to be an oxidizing process for the partial refining of the lead button that is produced from the fusion process. Once the lead bead is broken from the slag material, it is hammered into a cube-like structure, placed into a muffle furnace at 950 degrees centigrade for 30 to 40 minutes. The oxidizing reaction produces molten lead oxide, which is absorbed by a cupel. This cupel is a porous pot used specifically for this purpose. Some of the lead oxide and other gases are removed due to their volatilization characteristics. This leaves a more purified button which will contain the gold, silver, and platinum group metals if they are present. The silver will be present and alloyed with the gold. The platinum group metals may or may not be present, and if so, in small, minute quantities. This small little lead-free bead is further referred to as a prill or a door bead. After cupellation, the resulting door bead still requires further processing. The gold and platinum group metals need to be separated from the bead. In other words, the silver and the PGM group of metals need to be parted from the bead. At this point, there are two options available. The first is to part the bead with a slightly warm diluted nitric acid, or if the gold, silver, and platinum group metals are of a low concentration, then dissolvement will be necessary for analytical analysis, meaning concentrations are too small for any physical recovery. The parting is completed using parting cups that are designed for this process or by using glass beakers. After parting, the beads are decanted from the solution and washed with distilled water. If concentrations are large enough for the recovery, nitric acid is used. Since gold is a noble metal, it will resist the nitric acid, and the silver, etc. will be dissolved into the acid. The acid solution containing the silver is saved, as the silver can be recovered later. The gold will remain. The purity of the gold will differ depending on the amount of silver is concentrated in the bead. This will be explained in a future presentation when cupellation and parting will be discussed in greater detail. The parting process, if completed efficiently, will produce a gold bead that can be up to 3 to 4 nines fine. There is, however, one more step in the process, and that is annealing. Once the silver has been parted from the bead, the result leaves the bead as amorphous in structure. This means that the bead will be filled with minute holes throughout from where the silver has been dissolved. The gold bead will not be a single piece of precious and noble metal. Annealing results in a solid piece of metal. It is accomplished by placing the bead into a scorifying dish or small crucible and heating it to roughly 800 degrees centigrade for about 10 minutes. Structurally, the bead will slightly melt internally, filling in those small, minute pore spaces, resulting in a solid structure, after which all of your beads can be melted and poured into a single wafer or bar of purified metal. The whole fire assay method revolves around four principles. The first is the high degree of solubility. That is to say that the precious metals have a high degree of solubility within the molten lead, but is insoluble in the molten slag. It can be said that the lead becomes the collector of the precious metals and the slag is the collector of the gangue or garbage material. The second principle is in regards to the two molten solutions. It is the difference between the solution's densities. The slag density is lower than the lead and therefore will float on top of the molten lead, allowing for the easy separation of the lead bead from the gangue material when it is cooled and solidified. The third is that the lead can be completely removed from the lead bead by way of the oxidation fusion, referred to as cupellation. It uses the methodology of differential filtration. The lead bead is oxidized to lead oxide, which is absorbed by the cupel, leaving the precious metal bead intact. The last principle involves the parting process, where the nitric acid removes the silver. This principle is based on the fact that the silver is soluble in diluted nitric acid and the gold is not. Fire assay has been a popular tool for hundreds of years. It is a method which allows for the quick separation and elimination of all the associated gangue material from the precious metals. It does so at a lower cost compared to other methods. Larger samples and concentrates can be used. Larger samples in reference to analysis allows for a more accurate and analytical result. It also allows for a larger amount of refinement when dealing with high-grade ores or concentrates. Last, but probably not least, it's a very effective method of precious metal collection within a single crucible fusion. There are advantages for using fire assay as a preferred tool. This is because it's a total extraction technique, which accommodates for larger sample weights. Besides being a good and effective pre-concentrating technique for those precious and noble metals, it is a cheaper method in the long run compared to other techniques such as solutions chemistry. As with everything that has an advantage, there must be a disadvantage. With fire assay in a laboratory setting, skilled and experienced staff are required. For the small miner and/or prospector who wishes to do some collection and refining, as well as some analytical study as well, all one needs is some knowledge and experimentation. In a laboratory setting, one continuously works with hot furnaces and pots of molten metals. There is a risk of heat stress involved. If conducted outdoors using small portable furnaces, this is not so much a problem other than the possibility of one burning themselves. There are other health and safety concerns as well. If improperly handled, lead and lead oxide can be a major health risk. Proper personal protective equipment is a must, as well as good ventilation. Safety breathing masks with the right canisters must be used, as well as face shields. Now, cost can be a major contributing factor. Once all the equipment is purchased, operating costs do go way down. But it does cost quite a bit to stock up on consumables and equipment purchases, with the biggest expense relating to furnaces that are efficient and controllable. This brings us to the end of this presentation. It is part one and the introduction to this series on fire assay. My topic now is just a primer of what is to come in the future. I mentioned in the introduction, which is presented and geared towards a small miner and or prospector. In part two of this series, I will be talking about some of the equipment and reagents, that is the chemicals used for fusion and cupellation, and also include scorification. The reagents are better known as fluxing material or just plain fluxes. The next presentations will be geared towards the small enterprises. However, there may be some reference to laboratory analysis. I would like to say thank you for watching. If you found this introductory presentation informative, although a little bit dry, feel free to pass the link on to anyone else whom you feel may be interested or may benefit from this presentation. If you have any questions, Feel free to email me at bme@boykomineralexploration.com. I have also made this presentation free to download. Again, I'm Rob Boyko, Boyko Mineral Exploration.